Hey guys, Mr. Backberg here. In this video, we're going to look at optimization examples from economics. Now, there are a lot of places where calculus overlaps with economics, but two specific places that we're going to take a look at include maximizing profits and minimizing average costs. Now, we're going to suppose that R of X represents the revenue from selling X items. We're going to assume that C of X is the cost of producing X items, and then our profit, P of X, is going to be that R of X value minus that C of X value. So that's going to be the profit from selling X items. Now, as we're looking at marginal revenue and marginal cost and marginal profit, we're really looking at the derivative of these functions for specific X values. So the marginal revenue is the derivative of your R revenue function with respect to X. Your marginal cost is the derivative of your C function with respect to X. And then your marginal profit is the derivative of your P function with respect to X. Now, as far as maximizing profits, a maximum profit, if there is one, will occur at a production level where the marginal revenue, so the derivative of the revenue function, equals the marginal cost, so the derivative of the cost function. Now, we do want to be a little careful as we're looking at calculating maximum profits. One thing that we do want to keep in mind is the break-even point between our revenue and our cost functions. So the break-even point is when your costs and your revenues are exactly equal to each other. Anything to the right of there, you start turning a profit because then your revenues exceed your costs. But anything to the left of there, you're losing money because your revenues haven't caught up to your costs yet. So if we find a place where our cost derivative is equal to our revenue derivative to the left of our break-even point, then that's actually going to be a maximum loss of money. But then if we find a point where the cost derivative and the revenue derivative are equal to each other to the right of that break-even point, then that's our maximum profit level. So in this example, we're going to look at maximizing some profits. So suppose that your revenue function is 9x and your cost function is x cubed minus 6x squared plus 15x, and that x is going to represent thousands of units. So if our x value was 1, that would be 1,000 units. We want to figure out if there is a production level that's going to maximize profits, and if there is, then we want to figure out what exactly that x value is. Now, the first thing that I'm going to do is actually graph these out on my calculator. We talked about a break-even point where our costs and our revenues are exactly equal to each other. So I want to find that break-even point so that as we go through and set these derivatives equal to each other, we know whether we're finding a maximum profit level or a maximum loss level. So in my calculator, I've got that cost function and that revenue function typed in. I did have to adjust my window a little bit to be able to get a good picture of this. So for my x min, I went 0. For my x max, I went 5. For my y min, I went -10. And for my y max, I went 50. Now when I graph this out, I get a picture that looks something like this. So this first intersection point right here is the break-even point between these two functions. Now, if I wanted to actually find what that point was, I could do second calc and option number 5, intersect, and then I'm going to move this cursor over by where this intersection point happens, and I'll hit enter 3 times. So that intersection point happens at about 1.27-ish. So as we find the derivatives of these functions and set them equal to each other and solve, if we find a place where these derivatives are equal to the left of 1.27, then that's going to be a maximum loss. And if we find a place where their cost derivative and the revenue derivative are equal to each other to the right of 1.27, then that's going to be our maximum profit level. Now, as I'm looking at this picture, I do see that there's going to be a maximum loss level. So there's going to be a place in here where these slopes are parallel to each other. And it looks like visually it's going to happen at about 0.5 maybe. And then as I look over here on the right-hand side, I'm looking for a point, again, where the derivatives would be parallel to each other. And to me, it looks like there's a point happening at maybe about 3.5. But again, we'll do this using some calculus to find some exact value answers. So the first thing I want to do is find the derivative of each one of these functions. So let's start with that revenue function and do its derivative. We've got 9x, so the derivative of that is just 9. And then for our cost derivative, using the power rule a couple of times in here, drop the 3 down and we get 3x squared. Drop the 2 down and that's negative 12x. Take the x off of the 15 and that's plus 15. Now we're looking for where our cost derivative and our revenue derivative are equal to each other. So I'm just going to set these equal to each other. I'm going to go 3x squared minus 12x plus 15 is equal to 9. This is a quadratic equation, so I want to subtract the 9 over so that this is equal to 0. So 3x squared minus 12x plus 6 is equal to 0. It would be really nice if this quadratic factored out, but I don't think it's going to. So we're going to do the quadratic formula. So I'm going to do the opposite of the b value, plus and minus the square root of the b value squared, minus 4 times the a value times the c value, all over 2 times the a value. I'm going to start with simplifying things down underneath that radical. So we get 12 plus or minus the square root. Now if we do all of that math underneath the radical, I think we end up with 72. And this is all going to be over 6. Now the square root of 72 is actually going to break down. That'll turn into 6 root 2. So we've got 12 plus or minus 6 root 2 all over 6. Now both of these, the 12 and the 6 root 2, can be divided by the 6. 12 divided by 6 is 2 plus or minus. Now if we do 6 root 2 divided by 6, the 6's cancel each other out and we just get root 2. So one of our values is 2 plus root 2 and the other value is 2 minus root 2. Now if we were to type those into our calculator, 2 plus root 2 is going to be about 3.414 if we go to 3 decimals there. And 2 minus root 2 is going to be about 0.586 if we go to 3 decimals there. Now remember from earlier that break-even point was at about 1.26. And we said if we found a place to the left of that number where the cost derivative was equal to the revenue derivative, then that was going to be a maximum loss. So this 0.586, that's a point of maximum loss. And this x value of 3.414, that's going to be our x value for a maximum profit. So if we want to maximize our profits, we should produce 3.414 thousand units. Now the next thing we're going to look at doing is minimizing the average cost. So the production level, if there is one, at which the average cost is the smallest, is a level where the average cost is equal to the marginal cost. So the marginal cost we've already talked about is the derivative of your cost function, but the average cost is your cost function, so C of x, divided by x number of units that you're producing. So in this example, we're going to suppose that our cost function is the same exact function from earlier, so x cubed minus 6x squared plus 15x, where x is representing the thousands of units. We want to figure out if there's a production level that's going to minimize our average cost, and if so, we want to figure out what it is. So we've already done the derivative of this cost function. It was 3x squared minus 12x plus 15, but we also want to figure out what the average cost is. So we said that the average cost was our cost function divided by the x number of units that we're producing. So to do the average cost, I would take the x cubed minus 6x squared plus 15x, and we're dividing that by the x number of units that we're producing. Now all of these terms from the numerator can nicely get divided by that x. So x cubed divided by x is x squared. Negative 6x squared divided by x is negative 6x. And 15x divided by x is just plus 15. So I want to figure out where my cost derivative is equal to this quadratic function that we just came up with. So I'm going to take the 3x squared minus 12x plus 15, and I'm going to set that equal to the x squared minus 6x plus 15. I'm going to start moving everything over to the left-hand side. So if I subtract this x squared over, then I'm going to get 2x squared. If I add the 6x over, then I'm going to get minus 6x. And if I subtract the 15 over, those will cancel each other out. So now this is going to equal 0. To solve this, I'm going to factor an x out of the left-hand side. So we're going to get x times 2x minus 6 equals 0. These two factors equal 0, so we need to take each individual one and set them equal to 0. The first one is already solved, just x equals 0. But the other one, I'm going to add the 6 over, so 2x equals 6. Divide by the 2, so I get x equals 3. Now we want to remember that our x values are really representing thousands of units being produced. So having an x value of 0 doesn't really make a whole lot of sense, because that would say that we're not producing any units of whatever product it is. So I'm going to ignore that one. And I'm going to focus on this x value of 3. Now, before we can officially decide if this x value of 3 is actually minimizing our average cost, there is a little bit of extra work that we need to do. And what we're going to look at is this average cost equation that we got earlier, this x squared minus 6x plus 15. We want to check to see if this x value of 3 that we just got is actually an absolute minimum of this average cost function. So, to determine if something is a minimum or a maximum, we want to take the derivative of whatever function we're looking at. So if I do the derivative of this x squared minus 6x plus 15, then I'm going to get 2x minus 6. Setting this derivative equal to 0, again we get x equals 3. So we know that 3 is some sort of critical number. To determine if this is a maximum or a minimum, we can make a sign chart for this x value of 3. So if I were to plug in something to the left of 3, maybe I pick 2, plugging 2 into this average cost derivative, we would get a negative answer. And then if I plug in something to the right of 3, so maybe 4, plugging that into our average cost derivative, I would get a positive answer. So because our average cost derivative is changing from a negative to a positive, that means that this 3 is in fact a minimum point. So this 3x value that we got does indeed represent a production level that will minimize our average costs. That's going to be it for this video. Thanks for watching.